Hi Statistics, happy giant snowstorm. I hope that you are all staying safe and warm and you've gotten a chance to go sledding or play in the snow or relax or do something fun with some of your time off. This week you are going to be watching this video and then working on 2 practice sheets in addition to taking your quiz whichever day you're back in school this week. So we're starting to talk about normal curves. And I want to start by telling you the properties of a normal curve. This was from Sarah Steinberg and Sadie's presentation from before winter break. Every normal curve is bell-shaped, with the highest point over the mean. All normal curves are symmetric, and I'm going to be using the word curve or distribution sort of interchangeably here. So if I say normal curve, that means the same thing as when I say normal distribution. And they're symmetric about the mean, mu. So if you were to draw a vertical line through the mean, then you could fold the distribution in half over that and both sides would match up. So all normal curves have asymptotes along the horizontal axis. In other words, they always approach but never touch that horizontal axis. And they also never cross the horizontal axis. Finally, the area under the curve is equal to 1. So when we talk about areas under normal curves, we're going to be talking about probabilities, and the total area under the curve has to be 1. Another thing that you might see mentioned are the points of inflection of a normal curve. I think Unique and Abigail in calculus, you may have come across this term, but it's the place where the curve changes from being able to, say, hold water, so that's this section to the right could hold water, versus this section in between these 2 points would not be able to hold water. So these are called the points of inflection. So we have a bell-shaped curve. In the center of this curve is our mean, mu, and the points of inflection actually occur at very specific points, which are mu plus 1 standard deviation and mu minus 1 standard deviation. So we've got a bell-shaped curve, we have asymptotes along the horizontal axis, and if we folded this in half over that dotted line that I drew for mu, we should have it be the exact same on either side, so it's symmetric. Of course, my drawing's not perfect, but you get the idea. So then we're going to talk about the empirical rule. And this is a diagram that Sarah and Sadie showed you in their presentation. For this, I want you to note that we have our points of inflection at mu plus sigma and at mu minus sigma. We have mu right in the center of the distribution, and if we folded it in half, we'd get the same thing on either side. So notice that area between mu and the first inflection point represents 34% of the total area under the curve. And then that other set between mu and mu minus sigma is another 34%. So the total area between our 2 points of inflection is 68%. In other words, 68% of this curve is within 1 standard deviation of the mean, because we went 1 standard deviation to the right and 1 standard deviation to the left. Now let's look at 2 standard deviations away. We go to mu plus 2 sigma and mu minus 2 sigma. So we're going to add these areas on to our 68%. So we're going to do 68% plus 2 times 13.5%. And we're going to get 95%. So what we're seeing here is that 95% of this curve, 95% of the area under the curve is within 2 standard deviations of the mean. And you may remember that we have said that anything further than 2.5 standard deviations from the mean is unusual. So let's think about that for a moment. If 95% of the data is within 2 standard deviations of the mean, how much do we have left? 5%, right? And 5% is a small number. We're only 2 standard deviations away from the mean right now, not even 2.5. So 2.5 standard deviations from the mean means that we're going to have even less area under this curve left. Let's take a look at 3 standard deviations away from the mean. So we know from our past experience that a score that's 3 standard deviations away from the mean is going to be unusual. If we're talking about the area under this curve between 3 standard deviations away from the mean, we're going to take our 95% and add 2 times 2.35% to get 99.7%. 99.7% of the area under the curve lies within 3 standard deviations of the mean. So what's left over? We know the total area under the curve is 1, which translates to 100%. If we subtract 99.7%, we see that the remaining area is 0.3%. That's really small. So we have most of the curve covered between 3 standard deviations from the mean, this area that we're seeing here. Now we've talked about z-scores before. Z-scores are a way to measure how far a raw score is from the mean. So z-scores measure the distance of a raw score, that's just a regular data value, from the mean in units of standard deviation. And why would this be important? Well, let's look at what we just did. We just found areas under the curve based on how many standard deviations away from the mean we were. So if we can convert our raw scores to z-scores, we can start to find areas under that curve. The score for a z-score is x minus mu divided by sigma. Down here I have the definition of a raw score. It's a single data value from your set. So you've drawn your data, you have a bunch of numbers. You could find the z-score for one of them by just taking that number and plugging it into the z-score formula. Now, the standard normal distribution is a type of normal curve. I think Sarah and Sadie did a really good job explaining this in their presentation, where they showed you a normal curve first. Let's say here's a normal curve with a mean of 70, and let's say it has a standard deviation of 10. Then our points of inflection would occur at 80 and at 60. So this is just a regular normal curve. The standard normal distribution, or the standard normal curve, standardizes any other normal curve, like the one I just drew, and changes it so that our horizontal axis is not in raw scores, but is in z-scores instead. So what's the distance of the mean from the mean? That would be a distance of 0. 70 is a distance of 0 from the mean. We said that 80 was a distance of 1 standard deviation from the mean. And 60 was also a distance of 1, but it went to the left, so we're going to call this side -1. So the standard normal curve is just translating those raw scores into z-scores using the formula z minus z equals x minus mu over sigma. The nice thing about the standard normal curve is that we can easily find areas under the curve that are in different denominations. So when we looked up above at the empirical rule, we were looking at really sort of rough areas, right? We're talking about 1, 2, and 3 standard deviations away. But what if a z-score is half of a standard deviation away from the mean, or 2.5, or some other number that's not one of these whole denominations that we have? Using the standard normal curve, we can actually find those and this table below. So what I want you to first notice about this table is that it's areas to the left of z. So we have this diagram here. Anytime you're looking up an area to the left of z, right? Here's our z-score. We're talking about this area to the left of it. The second thing I want you to notice is the z column. So we have z here, and you're going to look down first. And then you're going to follow along to the right to match up your score to get the proper decimal. So let's say I wanted to know the area left of negative 2.5. So I recommend you always draw your normal curve first. And, it's a rough sketch. So here's our mean mu of 0, a z-score of 0. And now we're talking about a z-score of negative 2.5, and we want to know the area to the left of that. So in the table, and this is negative 2.50, I'm going to go down first to negative 2.5, and then I want to match that with the appropriate number across the top. So I said this was negative 2.50, which means I'm going to take this one and go down until I find the number that aligns. So that's 0.0062. That's the area to the left of a z-score of negative 2.5. Now, had this been, say, like negative 2.59, across the top, I would have gone to 0.09 and then come down to match up with the negative 2.5 side. So you're breaking these numbers, sort of like a stem and leaf plot, right? Where your stem is the first two digits that go over the decimal, right? And then your leaves are up top. So you want to match up your stem and your leaves. Now notice in this table, we only have negative numbers. What if you want to find the area to the left of a positive number? So let's say in this case I want to find the area to the left of, 3.17. So I'm going to draw my curve to get a visualization of it. Here's my mean with a z-score of 0. 3.17 is pretty far out there. And I want this area to the left of it. But my table can only tell me the area to the left of negative 3.17, which is way over here. So the table's only going to give me this area. How do those two things relate to each other? Remember, the curve is symmetric. So this area that I've drawn to the left of negative 3.17 is the same as the area to the right of positive 3.17. And you should keep in mind that the total area under the curve is 1. So I could find this area to the left of negative 3.17, which is the same as the area to the right of positive 3.17. And I could say 1 minus that area is equal to the area to the left of positive 3.17. So I'm going to find negative 3.1, and then I'm going to go over to 0.07, and I'm going to do 1 minus that number. So 1 minus 0.0008 is going to give me the area to the left of positive 3.17. And it should be a number that's pretty close to 1, because that's a lot of the area under that curve. And I see it's 0.9992. That's a lot of the area under the curve. That's 99.92% of it. So that's the area to the left of positive 3.17 that I've shaded above in blue. By the way, this table is in the practice packet for standard normal curves. So you have a copy of this table if you print that practice packet. Okay, here's the final example I want to show you. Let's say you want the area between two numbers. So let's say I'm going to look at negative 1.15 and 2.57. And I want to find the area between these two. So I'm looking for that area. How am I going to find that when I can only find the areas to the left of negative numbers? Well, first let's think about this. If I take the area to the left of 2.57, if I take the area to the left of 2.57, I'm talking about all this area, which includes the area to the left of negative 1.15. So in order to get the space that's just between them, I need to subtract that area to the left of negative 1.15. The area between negative 1.15 and 2.57 is equal to the area to the left of 2.57 minus the area to the left of negative 1.15. Which of these is going to be the easier one for us to find? The negative 1.15, because we've got the negative numbers in our table. So I'm going to go down to negative 1.1, and then over. That's 0.00, 0.01, 0.02, 0.03, 0.04. Here's my 0.05. What am I going to have to do to find the area to the left of 2.57? Well, this is like the last example. I'm going to have to do 1 minus the area to the left of negative 2.57. Negative 2.5, and then 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6. Here's 0, 7. So the area to the left of 2.57 is 1 minus 0.0051, which is 0.9949. So I'm going to find that area between now. Negative 1.15 and 2.57. We said that's going to be the area to the left of 2.57, which is 0.9949, minus the area to the left of negative 1.15, which is in our table 0.1251. And I get 0.8698. 86.98% of the area under the curve, and this is under the standard normal curve, is between negative 1.15 and 2.57. The next thing that you're going to do after you've taken all of these notes and reviewed them so you're sure you understand, is you have 2 practice sheets to complete this week. They're both on our Google Drive shared folder. And you can get to them by going to our shared folder, choosing probability, then going to the one that says normal curves, the subfolder, normal curves. The 2 practice packets for you to work on this week are practice with normal curves and practice with the standard normal curve. I'm expecting that if you have any questions from this video about the notes that you've taken, or if you have any questions about either of these practice sheets, whose answer keys are on Moodle, that you will be in contact with me. That means you either email me or you come to my office hours on Thursday morning from 7:45 to 8:45. I hope to hear from you or see you then.